All right, so welcome to lesson 3.9. In this video, we're going to talk about how we represent the three types of radioactive particles that we talked about in the last lesson. So in the last lesson, we talked a little bit about alpha, beta, and gamma decay and how we represent them as symbols and what can block these three types of radiation. Right? So radioactive decay is just a process of how we end up getting these particles that shoot out of specific isotopes. And there's two ways we can represent them. So we can represent them as sort of a model of what each isotope and particle looks like here. Or more commonly, because this will take a long time to draw, we'll represent them as a nuclear equation. So if alpha decay occurs, or any type of decay, notice that we all start out with an unstable isotope, right, that I circled in orange. So whether we've written out as a symbol or we have it drawn out as a model, what we start out with is called the parent isotope. All right, so let's record that in our notes. So this is our parent isotope, right? So oftentimes, if we have an unstable parent isotope, it's full of energy. It's gonna have so much energy that it splits off and shoots off a particle that I've circled in pink. So it can shoot off an alpha particle, which is also a helium atom, a beta particle, or an electron, or pure energy, this gamma particle here. So I can either represent it as this drawing or as these symbols here. So again, in pink, this one is called a particle. Right. And the last thing you need to know is that here, what you have left over after the parent isotope shoots off a particle, right? Here in green, represented by these models, or the symbols, is what I call, or not I call, but what scientists call the daughter isotope. So it's what you have left over, right? And a reminder that oftentimes we write them in what's called a nuclear equation, right? So we don't really use like the letters A, Z, and X every single time for the orange circles or the green circles. They're just a general formula of how we represent a nuclear equation. So let's talk first about how we use nuclear equations in order to identify the type of decay we have, whether it's alpha, beta, or gamma. And then let's talk about how we can use these equations to predict what daughter isotope we could end up with. Okay, so before we get to those types of practice problems, just a quick check-in, can you identify the parent isotope, the particle, and the daughter isotope in this example? Go ahead and pause the video and then unpause when you're ready. Okay, so hopefully just like from before, you might have noticed that the first isotope is the parent isotope, and then it splits off. This one is the particle. So usually the objects or isotope with the smaller atomic mass or the smaller top number after the arrow is our particle, and then what's left over is our daughter isotope. Another way we can tell if we have our notes handy with all three of the isotopes, we can quickly identify which one is the particle. So for example, if I did not know which one after the arrow was the particle or the daughter isotope, right, I could look at my notes that I've written here on the right-hand side, and I might notice that, hey, 4,2He is this one. So this is a representation of an alpha particle. So this one has to be the particle, right? Okay, so I'm going to use the same principle from the previous slide to help me figure out what type of radioactive decay each of these nuclear equations are, right? So mainly I need to figure out, okay, this equation, is this alpha decay, beta decay, or gamma decay? And the way I can tell is kind of just like what we did before, right? So looking at my nuclear equation, especially after the arrow, I'm going to look for the particle, right? So here I can see that I found the symbol 4,2He, and this is the same as the alpha particle. So therefore, this first one must be alpha decay, right? So this radioactive isotope has too much energy, it splits off. One of the things it splits off and shoots off is an alpha particle, and this is what's left over, known as the daughter isotope, right? And I can tell this is alpha decay, where it shoots off an alpha particle, because it is one of the products I make in this nuclear equation, right? It matches with alpha particle symbols. So the next two, see if you can figure that out on your own, and then go ahead and unpause when you're ready. Okay, so for this one, you might notice that this symbol looks familiar. 0, -1, and E standing for electron, mass is 0, and it loses one proton. So therefore, this one is beta decay. And for this third one, after the arrow, nothing here, 0, 0, and then this weird looking like V or Y symbol. So this one, I might notice that, hey, this is very similar or the same as the gamma symbol, right? So therefore, this third one is going to be gamma decay. And the second one we talked about earlier was beta decay. Right, so that's how I identify each of the types of radioactive decay. Okay, so what if I have a problem like this, where I start out with a parent isotope, an unstable isotope that's going to split off? And in this particular problem, it says, if the following isotope undergoes alpha decay, what will be produced? So I know that it's going to go through alpha decay, right? So there are a couple things I need to remember before I start this problem. One, on the left-hand side here, is I need to remember the symbols or representations for each of the three types of particles that we're going to focus on. And secondly, I need to remember that, hey, if we're talking about isotopes, it's flipped, right? So my atomic mass is on top, right? So this is the mass of the isotope. And my bottom number is the atomic number, or the number of protons that I have. Right, so once I know this, I know that, hey, just like before, this thing called PO, which I'll circle in blue, right? So PO is going to split off, and one of the things it shoots out is an alpha particle, and then whatever's left over is going to be my daughter isotope, right? So if I work backwards with these numbers, I can figure out what they add up to. Right, so for example, the massive PO is 210. And if I recall the symbol, the mass of He is 4. So whatever this is, something plus 4 needs to add back to what PO was before, 210, right? And then the same thing for the bottom number. You might find that this is very similar to fusion. So if you think you can figure this out on your own, feel free to skip forward. But otherwise, I'm going to go through this example and slow detail. Right? So again, going to the problem, I know it undergoes alpha decay. So therefore, one of the particles that I make has to be the alpha particle with a mass of 4 and 2 protons, right? And the symbol He, because if I have 2 protons, I have a helium, right? And I also recall in this drawing that these two need to add it up back to 210, right? So 4 plus what will be 210? Well, I can think, oh, 206 plus 4 will give me 210. If I wasn't able to figure that out in my head, I can do this in reverse, right? So 210 minus 4 will be 206. And that's how I got this top number, right? So if you imagine that the top row is just one equation on its own, right? 206 plus 4 will give me 210. Well, how do we figure out the bottom numbers or the number of protons? It's the same idea, right? So here, PO has an atomic number of 84 on the bottom. And when it splits off, helium has 2 protons. So whatever's left over for the bottom number will be here, right? So 2 plus what will give me 84? Well, 2 plus 82 will give me 84. How did I figure that out? Well, I need to think what plus 2 will equal 84. Or I can also think 84 minus 2 will give me 82, right? So just working the opposite of each other. So now I know the atomic number and I have the mass, but how do I figure out the element symbol of this? Well, I'm going to have to use my periodic table or ptable.com. Right? So if I have 82 protons, using my periodic table, remember my elements go in order left to right from top row to bottom row, right? And our top number, this number up top, is our atomic number or number of protons on the periodic table, because here we're talking about elements, not isotopes. Right, so therefore, I'm going to look for the number 82 on here. So 82, 82, 82. There we go. 82. Element number 82 is Pb, or lead. So therefore, after this isotope undergoes alpha decay, it will make Pb, element number 82, also known as lead. Right. Okay, so go ahead and see if you can figure out this one on your own. Notice that the difference with this one is it undergoes beta decay. So instead of using the symbol for alpha decay, we need to use the symbol for beta decay, right? And then when you're ready to double check, you can quickly unpause this video and fast forward to the answers. Okay, so recall that beta decay is this symbol. So therefore, I know that this is one of my particles. And just like before, I'm going to work backwards to figure out 0 plus what will equal 210. Well, this one's pretty straightforward. 210 plus 0 will give me 210. Now, this one's a little bit trickier. Negative 1 plus what will give me 84, right? Or I can think of this as what number minus 1 will give me 84. Well, 85 minus 1 will give me 84, right? So I got 85 from doing this, right? And the reason why I use plus 1 is because we're using algebra, right? So this would be the opposite, right? Or you can think about it this way, 84 equals -1 plus something, right? So if I want to solve for that question mark, it's +1. I'll end up with 85 equals that number. So now that I have both the top number and the bottom number, the only one I need is the atomic number, or the number of protons, 85. And that will help me identify what elements I have. So looking at my periodic table, looking for elements number 85, it's going to be this one. All right, atomic number is 85, symbol is AT. All right, so therefore I have elements AT. If I undergo beta decay, this will be my daughter isotope.